Welcome to this new lecture recording. I hope things will work properly as Echo 360 has been updated. Didn't give me the usual beep. Apparently there's a new checkbox for live streams, or maybe that Echo 360 now allows us to have a live stream. I will investigate that for the next lecture. That would be great. So let me start talking about this week's quiz, the last quiz, unfortunately. I'm sure you're all very desperate to have no more quiz after this week. Easy quiz again, as of course you are busy with assignment 2 and you want to prepare for the final exam, so I don't want to make the quiz too hard. Like the previous quiz, like quiz 7, it's meant to make you practice classes, so nothing hard conceptually, just get used to the syntax. So this week we want to play with variation on lists. So assume that lists are circular. So let me show you what I have in mind. Let's say we have the list ABC. So, of course, we know that ABC are indexed. Well, let me move the quotes to do it more easily. Are indexed from 0 up to 2. And then if the list was circular, so ABC would be repeated forever on both sides, right? So we have ABC, ABC, forever, CBA, CBA, forever. And of course, indices would keep increasing as we move to the right. 3, 4, 5, 6, 7, 8, and so on, and would keep decreasing when moving on the left hand side. -5, -6, and so on. So notice that things work well, because C being of index -1 with this model, it's consistent with the way Python lets us index lists, right? So we know that we can index using positive indices 0, 1, 2, or using negative indices, and the last element has an index of -1. So that works nicely. It's consistent with this model, right? So now if we play with this model, if our list L is this rather than that, so we could have slices that involve elements which now have an arbitrary range, which can be any integers, right? So we could say we can go from -4 or from -5 to +8 excluded, right, in steps of 4. Why not, right? So we'd start with this guy, index of -5, and then the step being 4, we would add 4. So 1, 2, 3, 4, go to -1, 1, 2, 3, 4, 0, 1, 2, 3, sorry, 1, 2, 3, 4, let me get it right, 1, 2, 3, 4, -1 plus 4, that's 3, indeed. And 4 plus 3, that's 7. 1, 2, 3, 4, that's 7. Right, so that's all indices starting from -5, stopping before 8, in steps of 4, in which case that would return what we have an index -4, so B, then what we have at index -1, so C, what we have at index 3, A, and what we have at index 7, So B, right? So that's essentially what we want to play with. So as with usual lists, we can leave each of these three fields possibly empty, right? So the quiz explains, well, essentially it's what happens with the usual lists, right? So when the third field is left empty, it's implicitly one, step of one moving forward. When the first element is empty, it's usually 0, and when the last element is usually empty, it's the length of L minus length of L, right? We want to stop at the last element included, so it's the length of L. But it's a bit different when the that's what we have in case the step is positive, right? Because we want to move from the beginning to the end by default. When the index is negative, we want to move from the end to the beginning, so we reverse the rows of these two fields, right? So the quiz makes that very clear. So I insist on Ed that before you start the quiz, you have to spend enough time to read the comment to make sure that this is totally clear. I don't think there's any ambiguity, there is any gap, so make sure you read that carefully to understand exactly what these fields are supposed to be in case they are empty. Right, so you see, we can think of that as an extension of a list. We could actually extend the list class. So let me say a few words. We'll talk about classes that don't derive from object, but that derive from other classes in the next few lectures. But let me just say a few words about that. So I could define a new class, myList, right? That would be a child that would derive from, that would inherit from the built-in list class, right? So as opposed to this, which we have been working with so far, which is a class we define that derives from the mother of our class's object. Now we say we put something in between object and our class list, right? So we essentially want to inherit all the methods of list and takes them as they are, and in case we're not happy with them, re-implement them, change the definition, right? So Java programmers know what this means in the name of inheritance. This is this concept we are going to look at a bit, not much. So of course this class we define will have its own init method, right? So what should we do to initialize such a myList object? Well, if we think of a myList object as an extension of a list object, right, it makes sense to ask list to initialize first, and then we'll do the extra work, some extra work if needed, right? So we want myList to be a special kind of list, a more powerful or slightly defined kind of list, right? So the standard way of doing that is to call a special function called super. Here we could just do it the easy way, let list itself call init, right? But in case we have a more complex hierarchy, in case myList was not only a child of list, but maybe of other classes, which themselves would inherit from other classes, we could have a very complex hierarchy. Super would be smart enough to essentially travel along all the ancestors, all the classes above myList, right? so that they initialize the object one by one in turn at the right time. Okay, let's not get into that. I mean, now we just understand that to initialize a mylist object, that we want to be a particular case of list, an extension of a list object, then we want the parent of my list, namely the built-in list, to initialize first, and that's what super is going to do, right? So super will find that it should hand over to the parent to list, and finding whom to hand over, finding list, we want init to be applied, right? So now, of course, we have nothing interesting. We have essentially nothing but a list under different name, right? We have a class that inherits fully from list, so that means a class that has all the functionality, all the methods defined in list. All right, so if I create a mylist object, I get what list would give me, right? If I call list, I get an empty list, right? So same thing. And this mylist object now can has access to all the methods defined in list, right? In other words, mylist has a dictionary of methods, as we know. And when we call a method on a mylist object, we look in the classes dictionary for the method we're asking for. If we don't find it there, we're going to go up in the hierarchy. So see that we inherit from list, right? So let's see whether list has the method we ask for, right? So we have seen that before with new in particular, right? We say that when we create an object, we call this special method new, and we find it in object because object is just above, right? But here we don't have object just above, we have list just above. So we call append. We don't find append in mylist dictionary, so we look in the parent in list, and in list we find append. So hopefully that that works, and indeed that extends L with 3, and we can extend. We can use the extend method, range 3 to 7. Let's see what L becomes. Okay, extend it with 3, 4, 5, 6, and so on. You see. So again, now we don't, of course, implement this class just to have a different name, but to get either a different behavior or more functions, more methods, right? So for instance, we might not be happy with append, or we might not be happy with the way extend works, right? So my list would make append and extends behave in a very special way. So we would have to redefine, to overwrite the implementation of append and extend. Let's not do that. Let's just define a new method that now, let's call it double, that essentially extends a list with itself, right? So what do we want? We want the list we're working with, the object we're working with, to extend itself with itself, right? And now we should be able to call this method and see what L is. Okay, so we have essentially made a copy of what L happens to be at this stage and appended it to itself, right? And then, of course, keep using the usual methods. All right, so I think that's a particular case. A particular example of a class that's happy with all the methods defined in the parent class in the list, but that adds some functionality, that adds new methods. And as I said before, we could also redefine some of the methods in list if there is any good reason for that, if that's our purpose. All right, so that's not what the quiz is about, right? So this is of course very interesting, a very interesting technique to be able to extend classes. We'll see examples of that in the next few lectures. But for this quiz, we are working with a class. Where is it? Where's my quiz? Oh, there it is. Yeah, so you see, I don't make circular list inherit, derive from list, but a standard class that inherits, derives from object, right? So we don't use we don't use this technique. And now if we have a look at what we want to be able to create what essentially lists in a slightly different way, right? So you see, now we can provide as argument to init not just nothing, which would create an empty list, but any number of arguments, or here only one argument, here 5 arguments, right? In which case we create a list initialized as desired. And now we play the game of what I explained before, right? So assuming that this list is actually infinite in both directions, so I can talk of index 50, right? So what is at position 50? Of course, it's nothing but what is in this list at index 50 modulo 5, right? 50 modulo the length of the list. And I can assign to that, right? I can use this indices either to access elements or to assign elements, right? So here I want to assign 100 to my circular list at index 50. So I can think of that as essentially modifying this kind of structure, right? This kind of infinite structure at index 50. But of course, since I'm repeating the same pattern, let me make that a bit clearer, right? So now we have indices 0, 1, 2, 3, 0, 1, 2, 3, right? So it's essentially 3, 4, 5, 6, 7. Eventually, at index 50, I have a particular element of my list, 0, 1, 2, or 3. I want to change that to 100, right? But since it is the same pattern which is repeated again and again, of course, I want this change at that particular location in my circular list to be repeated at the corresponding position everywhere, right? Otherwise, it would not be a circular list anymore. It would be, it wouldn't be circular. It wouldn't be a pattern repeated forever, right? So, in other words, another way to say that is that if I work just with this list, I want to change at position 50% 5, right? 50% the length of my list, which is 0. Whatever I have now, which is 0, by 100, right? So that's what my list becomes. Right now, if at position at index, this index I assign 30, it means that at index this number percent length of the list 5, which is of course 3, I want to assign the value 30. So now at index 3 I have the value 30, right? And index minus 1, this is this, minus 2, minus 3, minus 4, minus 5. So minus this, of course, percent length of the list 5, that's minus 3, so minus 1, minus 2, minus 3. So I want to change this element to 20. Okay, so as you can imagine, when we work with this notation, with bracket notation, either to access an element like we do next, or to assign an element, we implement a special method, right? So just, I didn't tell you which one, but just make a Google search, and in 2 seconds, you will find out what special method we implement. We know that when we print an object, right, we call the special method _str, right? We have seen this method already. We know that when we call the len function, we call the special method _len_, right? Which I think I write, yeah, I asked you that, right? So you have to implement this special method, len surrounded by 2 underscores on both sides, right? So same thing when you assign to your list by index, right? You use special methods to find out which one, and then straightforward. Now we are only going to assign to particular members of the list, so to use between brackets only an integer, right, for assignment. When we look at the values, then we know that we could also assign using a slice, right? So we're not going to use slices for assignments. We're going to use slices only for looking at elements to get parts of the list, right? So now when we have a list L, this time I define the list consisting of all numbers from 10 up to 19. Then we can look at elements, not change them, right? Look at them using indices. So same thing, right? You understand now that this means 3, 23, 13, 23. So modulo the length of the list, so 10. So each time you get to the element of index 3, 13. Minus 7 is also equal to 3 modulo 10. So we get the same thing, right? Etc. etc. But also, now we're also going to retrieve not just elements of the list with bracket notation using just an integer, but slices, right? So sublists, right? So that's essentially what I showed you before, right? So heaps and heaps and heaps of tests in this quiz, so that we are very clear on how to interpret slices. And by the way, you're probably going to find notes number, which notes? Notes number, card shuffling number 9, I think. Useful, right? Because these talk about slices. Yeah, so probably some useful stuff in these notes in relation to slices, right? So you see the first, so you need to do a number of things. You need to find out which special method to implement when retrieving the value, what's different to assigning. When you assign, like here, when you assign some value to some member of the list, to somewhere in your list, it's a special method. It's another special method in case you don't assign, but you look at what's at given location, right? Another method, and on top of that, this method can accept either an integer, index, or a slice, right? So the method has to be flexible enough to allow for both uses. And when it's a slice, the logic is exactly what I explained before. It's exactly given by this, right? So I gave you the example of the slice -584. So it's lots of talk, lots of blah blah blah, but actually this quiz is pretty straightforward. So it's interesting because it will make you practice class syntax and get an appreciation of the special methods. But otherwise, conceptually, it's pretty simple. So you should not spend too much time, hopefully, and you can focus on the assignment and prepare for the final exam. And as usual, if you need, if you would like to talk to me, then you're welcome to join Microsoft Teams at the usual link. Nobody joined yesterday, but I will be logged in. I will be in touch tomorrow, if you like, at 10 p.m., at 8 p.m. All right, so now let's move to the next topic for tonight, which is notes number 23, because that's essentially part of the assignment, right? So if you had a look at all the posts on Ed, I mentioned that a few times, that you were able to do a lot, but at some point you have to determine the LCS, right, of two files, namely what are the longest, biggest, if you like, common chunks in two files. And this is not defined in a unique way. Biggest, that's unique, right? So you find out that you have 6 lines in common between two files, in the same order, of course, right? Not in one ordering in one file, different ordering in the other file, but line 1, line 2, line 3, line 4, up to 6, somewhere in this order in file 1 and file 2. And so 6 is fixed, but these 6 lines could be different, right? And for every solution, for every chunk of 6 lines common to both files, we'll have a different diff, set of diff commands. So that's the second part of the assignment, and essentially exactly the problem we want to look at tonight. So we have to take our time to understand that very well, develop the solution. Of course, the code is nicely and it's written properly in a very clean way in this file, and you can just copy and paste and modify. You just need to modify this code a bit to adapt it to the task of assignment 2, but it's essentially the same problem. Okay, so before I jump into this particular problem that is the topic of these notes, so let me introduce what this is all about. So it's about a programming technique called dynamic programming, which is very similar to recursion. Actually, you can think of it as recursion bottom up, as opposed to recursion being top down. So let me clarify that using another example. Let me talk about another particular problem. You will see as a practice exercise, right? So another way to justify, to introduce this programming technique. Right, if you want to give someone, to give change for someone, if you want to give someone a given amount of money, $259, right? And you want to minimize the number of banknotes and coins you give to this person so that they amount to $259, right? So we assume that we have only banknotes of value $100, $50, $20, $10, $5, banknotes and coins, $2 and $1, right? Plus, we also assume that, like the Bank of Australia, we can print money at will, so we have an infinite amount of each of these values, right? So infinite number of 100 banknotes, $100 banknotes, infinite number of $50 banknotes, and so on. Right, so how can we give the minimum number of banknotes and coins? Well, we're going to go for a greedy approach, right? So we're going to look at the maximum value we have, which is 100, that fits into 159, and we can fit $100 twice, all right? And now we are left with $59. So then we look at the next value we have, which is 50. How many times can we fit 15? 59, only once. So we are going to give one $50 banknote, and we still owe our friend $9. $20, that doesn't help. $10 doesn't help, but $5 reduces our debt to $4. And now with $2 coins, we are done. All right, so altogether, I should have written that next. So 1, 2, 3, 4, 5, 6, right? So 6 banknotes and coins were sufficient and necessary, right, to reach this amount of $259. So in this case, the solution is unique, right? It's a unique solution, not only in terms of number of banknotes and coins, but also what are those banknotes and those coins. So interestingly enough, this greedy approach, right, you understand that we're greedy because we try to use as many as we can of the highest values, right, and then make our way to lower and lower, smaller and smaller values. Okay, so this greedy approach works because of this very particular distribution of values, 100, 50, 20, 10, 5, 2, and 1. It's not arbitrary. It's a sequence of values that allows this greedy approach to work, right? Because now assume that we have only banknotes of coins of value $1, $20, and $50, right? And we want to give our friend an amount of $60. Well, if we're greedy, what do we do? Well, of course, we can. So again, we assume that these amounts are available in infinite quantity, right? So we have as many of those as we like. So we can fit 50, right? So 50, which reduces our debt to 10, but now 20 doesn't help, is too much. So we are left with giving 10 times $1, right? So 50 plus 10 times 1, that's 60. So altogether, 11 coins and banknotes, which of course is not optimal, right? Because if we gave 20 times 3 banknotes of $20, that would be 60, right? Which is better if you want to minimize the number of banknotes and coins. So you see, the greedy approach doesn't succeed with this particular set of values. And interestingly enough, you might think it's not a difficult problem to find, to identify, to characterize the sequence of values for which a greedy approach is possible. Always works, but it turns out to be a very complicated problem with no good, clean, closed solution, right? So it's interesting. Sometimes simple problems don't have simple solutions at all. Right, so you see, if now our so the problem of minimizing the number of banknotes and coins that amount to a given sum is made more complex, first by not using the standard values, which have a very special property, namely that the greedy approach works, but an arbitrary sequence of values that makes it harder. And then, of course, we can make it also harder by assuming that we don't have an infinite number of these values, which is totally unrealistic, but our means are limited. So we have only some number of banknotes of value 100, some number of banknotes of value 50, and so on, and we have to do that, right? So that's the second way to make the problem more interesting and more complicated. So, right, so assume that you have these values. Let's still take $1, $2, and $5. That's only values we have. It's arbitrary, right? And then let's assume that we have those in some quantity, right? So we might have only, we have maybe 4 of those, we have 1 of that, we have 3 of that, right? So of course we won't be able to give much, we won't be able to be very generous, right? And we want to find out what is how we can get a solution, how we can get how can give someone, let's say, $10, right, with a minimal number of coins, right? So probably is to give someone $10 if we can, thanks to what we have, eventually minimizing the number of coins. And if we have many solutions, many ways of doing that, we would like to have more solutions or combinations. So if you think recursively, you see, I guess you will reason as follows. You say, well, to get $10 eventually, I need to get close enough to 10 and then be able to give $1 extra if I can, or $2 if I can, or $5 if I can, right? So either reach 9 or reach 8 or reach 5, right? Thanks to $1 or $2 or $5. If I go this way, right, then I need to be able to get eventually to get $9 thanks to what is available at this stage, which is only 3 $1 coins, 1 $2 coin, and 3 $5 coins, right? Because I'm using one $1 coin, so I've had one less to be able to get an amount of 9, right? And if that's the way I want to follow, then I need to get $8 thanks to having available 4 $1 coins, no $0 coin, and 3 $5 coins. And here that will be 4, 1, and 0, right? And you see how the so the recursion, of course, would now we have reduced the problem size from 10 down to 9, 8, and 5, right? So if we implement a recursive function, when we call the function with an input of 10, we're going to call it recursively on an output of 9, 8, and 5. And probably also these numbers, right? These numbers matter, so the input wouldn't be only 10, but 10 plus everything we have available, right? And then we reduce the problem size by having to put together a small amount, thanks to some coins available. So we could get a value of 8, or we could get a value of 7, or we could get a value of 4, right? But here we can get only a value of 7 because we have no $2 available, right? Or a value of 8 minus 5, which is 3, right? And here we can only get a value of 4 or a value of 3 because we have no $5 oh, no, sorry, it's not 0, it's 2. Right, so we can also go there, and that's it. So of course, when we reach 0, right, we are happy. And since we want the minimum number of coins, I guess that will be the unique solution, right? Because if you are able to reach 0 along other branches, of course, they will necessitate more coins, right? The number of coins is given by the length of the branch, right? So that's what we get in this particular case, right? But of course, for other values, other problems, other trees, right? You understand you will have a tree which might reach 0 for the first time, but many times at the same depth, right? In which case, this, and that will be the solution, right? Together with, of course, what you have on the path, which gives you, okay, which coins did I use, right? So I used 5, and I used 5 as well, right? So I guess if you build your tree properly, if your recursion is implemented properly, you will get at the same time not only the minimum number of coins, but also all possible ways to give that many coins and get the amount you want, right? So in other words, you see, you are looking for a given, the smallest depth that gives you a value of 0. The number of zeros at this depth is the number of solutions, and the solutions themselves are probably to be read from some appropriate labeling of the edges of the branches, right? Something like that. And of course, you could have no solution, right? It might be that no branch ends with 0. I guess you stop when the number, you don't want to get negative number, of course, even though we have negative interest rates nowadays, but that's pretty unconventional. So in conventional finance, all amounts are positive, right? So all that to say that if we solve the problem recursively, you see, it's a top-down approach, right? So our aim is to get a sum of $10, right? And we reduce this sum of $10 to something a bit smaller, right? We get closer to the solution by using our resources in some way, right? And the use of these resources reduces the problem of size 10 to a problem of a smaller size, 9, 8, and 5. And this is done again and again and again until you reach base case 0, right? So top down, that's the nature of recursion. So the technique we look at today is dynamic programming, is bottom up. So it's not much difference. It's interesting to think really in depth on what is different between both methods. It's not totally obvious. So I let you reflect on that. I just explain to you the methods, but I let you reflect on the difference between bottom up and top down. So if I take the same example as before, so 1, 2, 5, 4, 1, 3, 1, 2, 5, 4, 1, 3, a bottom up method essentially, oops, I think I can show things properly this way. Nice. right? So yeah, we're going to find solutions to get an amount of $1, $2, $3, $4, right? So bottom up, right? From the smallest amounts to the largest amount. And of course, our aim is to get to the desired amount of 10. So we'll build solutions up to 10, which is our target, our aim. Right. So how can we get a sum of $1? Well, by using a $1 coin, right? So we can get there indeed with only one coin, right? And what's left would be 3 $1 coins, 1 $2 coin, and 3 $5 coins. Okay. How can we get $2? Minimally. Well, of course, we could use solutions we have for a small amount, here only $1, and complement those solutions, right? So we have indeed a solution to getting $1, namely by using a $1 coin, and we can complement this solution with a second $1 coin, and we can because we have 3 left, and then we will use 2 $1 coins, right? But we can also just use a $1 coin. And since we want to get the minimal number of coins, we're just going to consider this solution, right? So consider just one coin, namely a $2 coin, and then 4, 0, 3. Now, how can we get $3? We can get help from either solutions to get $1, adding $2 if we can. Yes, you can. Yes, we can, because we have here a $2 coin, or thanks to solutions to $2 if we can. Can we? Yes, because you just need to add $1 coin, and we have 4 left. All right, so here you see we have solution with 2 coins, one coming from the $1 solutions using an extra $1 coin, so we'll have only 2 $1 coins left. Or thanks to solutions to $2, I messed up again. Well, yeah, from here to there, I'm adding $2. Right, I'm adding $2 to $1, so this decreases by 1, so 303. Or I'm adding $1 to solutions to $2, which I can, and so I will be left with 3, Jesus Christ, 0, 3. Right, so you see, I build this structure, right, by having first for each of these amounts the optimal solution, right, and together with what the solutions are in terms of how much is left. And of course, if you know how much is left, you know how much you have used, right? What you have used is the complement. So here 4 minus 3, 1 minus 0, and 3 minus 3. So 1, 1, and 0, right? And on you go, right? So of course, sometimes you will be stuck, right? So for how can you get to $4 optimally? Well, obviously by adding $1 to 3, so that will give you a solution, right? With 3 coins, but you will have no solutions from thanks to 2, because you have a unique solution for 2, which leaves you with no $2 coin, and you have no solutions from 1 because you have no $3 coin, right? So you see that more and more generally, right, as you build your table, if you have this amount, if you have built your table up to this point, right, if all that has been built, and you have a particular amount x here, then you're going to look at whether you can get x thanks to x minus 1, because your coins are 1, 2, and 5, right? Thanks to x minus 1, or thanks to x minus 2, or thanks to x minus 5, right? That's all options you have possibly, right? And in case you have no solution there, if in case this cell is empty, because you couldn't get this amount, then of course this hope is lost, so nothing will happen, right? In case you have at least one solution, you might have many solutions, right? So you need to look at, for each of these solutions, whether you can complement it to get x, right? So if you have 3 solutions to x minus 1, you also know how many $1 coins are left, if any, right? So if nothing is left for this solution, then that's useless, right? But if one is left, then you can use that solution and complement it, right, with decreasing the number of $1 coins there by 1, right? If you have at least a $1 coin in this solution, then you can also complement it by decreasing its number by 1, use a $1 coin to get x, right? And same thing will happen with x minus 2, right? So you look at all the solutions you have, if any, plus you look at all those which have at least a $2 coin left, otherwise you can't use them. But if one is left, has at least one $2 coin left, then you can use it and complement it, right, to get solution to x, and same thing for there. And not only must you have to be able to complement your solution, right, if any, but on top of that, you have to be optimal, right? So in case you can get a solution from x minus 2 and from x minus 5, but if all solutions to if the solutions to x minus 2 use 6 coins, whether the solutions to x minus 5 use 5 coins, then of course, and if you can complement this solution, then of course you're going to use only that one, right, to get an optimal count for x of 6. Because if you use solution for x minus 2, you would go up to 7, right, which is not optimal, right? So you see what enters the stage, right? What's involved. So you look at the amount you want minus each of the amounts you might have, right? And then the question is, for each solutions for these amounts, can I extend it with the appropriate value? And on top of that, in case I have many solutions, right, I want to only keep those which are optimal, so those that minimize, right? And eventually you are going to get to 10, which is the sum you want. And you will know both how many coins you need for that, so how many coins are necessary and sufficient, and for this number of coins, what are the combination of coins that you can use. Okay, so that's an exercise for you to practice. But today, in these notes, we look at another problem, which is the Levenstein distance, so which answers the question, how are two words similar, right? So, and it's of course a very practical problem, right? When you type something, a word on your phone, your laptop, a number of suggestions might pop up, especially if you mistype something, right? So how do we make these suggestions? Okay, if you type hello, right? I guess you get a suggestion. Are you sure you don't mean hello, right? Why hello and not goodbye? Well, of course, because hello it's much closer to hello than goodbye, right? So suggestions either to complete a word or to fix a typo, right, are going to be based on similar words. Right? So how do we measure the similarity between two words? How do we find the distance between hello and hello, and the distance between these two words? Right, that's what we want. And if you think about it, right, so we use in these notes two examples, leopard and what is it? I don't even remember. And depart, yeah. And depart. Right, so how do we measure the distance between, for instance, words which are a bit more different than hello and hello, leopard and depart? Well, obviously, you can observe that you have a number of letters which are identical in the same order, right? So that tells immediately that this is exactly the same problem as the diff problem of assignment 2, right? Instead of working with lines in the file, we just work with letters in a word. That's all. That's the only difference. Otherwise, it's the same problem, right? So if we match what is common between leopard and depart, we see that before this common E, we have on one hand L in one word and D in the other word, right? Between E and P, we have nothing in the second word, that we have O in the first word. And again, at the end, you have two letters that differ. So to measure the similarity between leopard and depart, we might think of counting the number of transformations we need to convert one word into the other. Right, so how many transformations do I need to apply to leopard to transform it into depart? What transformations can we consider? I guess it's pretty, of course, it's up to us to decide what the transformation is, but it's natural to consider, following this example, deletions, right? So deleting a letter in the first word, deleting a line, of course, in file 1. Here we don't need to insert letters, but as you can imagine, for other examples, you might have to add a letter to the second word, or to change a letter into another one, right? So that's the three possible transformations. Delete a letter in the first word, add or insert a letter in the second word, the word you want to get to, and change a letter into the second one, right? And if we want to compute the distance between both words, of course we could count the number of transformations we need to apply, but you can also say that some transformations are more costly than others and give them a particular cost, in which case the distance won't be the number of transformations, but then the sum of the costs of all the transformations you're applying, right? And obviously, to change L to D, you can also delete L and append D, right? So any change can be achieved by a deletion plus deletion on the left, deletion in the first word, and an addition, insertion in the second one, in the second file, right? So either you think that since the change is exactly this can be achieved thanks to deletion and an append, you give to a change the cost, which is the sum of the cost of a deletion additions. You might say this is worth 1, this is worth 1, this cost, sorry, this has both have a cost of 1, hence because of that C has a cost of 2. Or you might consider that actually it's nicer to do a change as opposed to a deletion followed by an insertion, or an insertion followed by deletion. So I make the cost less. I decide to make it 1.5 or whatever, right? So you have to decide. It depends how you want to model the problem, right? So either you consider since it's equivalent, the cost is the same, or it's nice, it's better to do this single operation as opposed to a sequence of 2 operations. So I want to favor a change to deletion plus append, so I make the cost less to go that way as opposed to go to this way, right? So let's play with this model, but again it's totally arbitrary, right? So let's say that we give a cost of 1 to D and A and a cost of 2 to C. And if that's the case, then we can compute the distance between leopard and depart, right? The cost would be, in case we change L to D, that's 2, plus if we go from here to there, right? So delete O plus 1, and then change D to T, so plus 2, right? 5. The cost is 5, and it's clear that we can't do any better, right? We can do much worse, of course. We can delete everything in leopard and insert everything in depart, right? So the cost will be how many letters? 7. 7 plus 6, so 13, right? That works in terms of transforming one into the other, but it's not optimal, right? So 5, if you think about it, 5 is the minimal cost. We can't do any better, right? And of course, it's not the only solution, because instead of changing, as we said before, you can either delete L and append D, or append D and then delete L, right? So not a unique solution, but all optimal solutions for a cost of 5, right? So what we call the Levenshtein distance between 2 words is this, is the minimal cost of transforming one way into another, right? So when you get as a suggestion hello, because the Levenshtein distance would be equal to 2, right? You just need to convert this K into a L, and no other English word, possibly, yeah, well, maybe there are other words, but I don't think of any. If probably no other English word has a Levenshtein distance of 2, right? In which case that would be the only suggestion to fix this typo, right? But in case you had other words which would be at the distance of 2, this would be added as alternative suggestions, right? It's a very practical problem. Right, so you see in the PDF, it's that way. I change actually depart to leopard, right? And you see I've got essentially for cost of 5, 9 solutions, right? So that's 1, insert L, delete D, insert O, insert D, and delete T, right? That's this solution, right? Then you have other solutions where you change D to L, when you insert O and change T to D. That's the one we described here, right? Right, so because of this, of course, as you can imagine, because we make a change equivalent to deletion and insertion, so that's going to multiply the number of solutions by 3 every time we have a change, right? Change can be either change or deletion and insertion, or insertion and deletion, right? So that multiplies the number of solutions. If we make the cost of change less, then the number of solutions, of course, will decrease as well. So how to do that? Well, so we could do that using recursion, right? Or we could do that using dynamic programming, which is the technique I just explained before, and you should be convinced that it's nothing but a variation on the coin problem, right? It's similar kind of problem. So we can use a similar kind of technique, except that here the cost, you see, was in relation to just one number, namely the final sum you want to give to someone, $10, right? So it was linear, it was a one-dimensional structure. But here the cost is in relation to two numbers, to data, right? Two words. So we're going to need a two-dimensional structure, right? So we are going to have in one dimension the first word. Doesn't matter, of course, which word we say is the first one, which word is the second one. It doesn't matter. Let's be consistent with the nodes. So the nodes, I keep forgetting. The nodes say depart into lipid. So we'll have D part and we have standard dot y lipid. Right. Draw nice lines. Good. Right. So similarly to, it's taken me years to find that I could draw straight lines. So I can't draw enough straight lines. Show a new skill. Right. So you see, with the coin problem, right, we were building the solution bottom up, right? So from small values to large values. Okay. So what is the counterpart to this in a two-dimensional array, right? Well, of course, the small problem will be in this area, right, around the lower left corner, and the big problem will be around that area in the upper right corner. Right, so what we want to compute is the cost of transforming an initial segment of depart into some initial segment of lipid, right? And of course, the problem is solved if the initial segments are the full words, right? So we expect to see the solution there in the upper right corner. Okay. So if you want to convert initial segment of depart, let's say depart into initial segment of lipid, let's say Leo, right? So we'll indicate here, we'll compute here the minimal way of doing so, right? So what is the minimal cost of transforming d bar into Leo? What is the cost? And then what are the ways to make this transformation at this minimal cost? Now it's clear that we have to eventually either so since the only transformations are to delete a letter in the first word, or insert a letter in the second word, or change a letter of the first word into a letter of the second word, right? It's clear that the last operation will be one or the other. So in case it is a deletion, that means that we have been able to map dep into Leo, right? We have been able to transform dep into Leo. So I've been able to go there, and then you need to map d par into Leo. We just need to, after that, to delete A, right? So for cost, which will be the cost you find in this cell plus 1. Okay, that's one way, if the last operation is a deletion. But you can also make the last operation an insertion, an append, right? Append O. So that's going to be possible if you have been able to transform d bar into Li, right, for a given cost, and to transform d bar into Leo. Then of course you need to just add O, right, for an extra cost of 1 compared to the cost of transforming d bar into Leo. And the last possibility is to perform a change if needed, right? So that's where things get interesting, because a change, of course, means moving diagonally, right? So it means you have been able to map dep into Li. Now, how can you map? How can you change d bar into Leo? By changing the new and last word in the long initial segment of the initial word, of the first word, namely A, changing that into O, right, for cost of this plus 2, right? That's of course because you need to perform a change, right? Because these two letters are different. But you see, if we were going there, right, because it's P horizontally, vertically, right? So if you are able to map D into a Leo, of course you can just map dip into Leop at no extra cost, right? So when you move diagonally in this case, you carry over the solutions for the same cost, right? There is no extra transformation to apply, right? So it means that, you see, we're going to compute the values in any cell, either by coming from the left for an extra cost of 1, or coming from below for an extra cost of 1, or coming from southwest, so moving diagonally up this way, right? Either for no extra cost in case the letters are the same, or for an extra cost of 2 in case the letters are different, right? And we're only going to keep, so for each of these 3 options, we only keep those which minimize the cost, right? So here, if you want to get to this point, right, if here the cost was 3, if here it was 3, if here it was 2, right? So you see, you get all solutions, right, which give you a cost of 4, right? So 3 plus 1, 3 plus 1, and 2 plus 2, right? So you get solutions coming from the left, from below, and from southwest. But in case the costs were equal to 3 everywhere, then you will only get solutions from the left and from below, right? That would be a cost of 3 plus 2, 5. It's larger, so we ignore that, right? If he had a cost of 2, then the solutions would only come from below, right? Because you would have an extra cost of 1, and coming from the left, 4 would be more expensive. Coming from diagonally, 3 plus 2, 5 would be even more expensive, right? So that's the basic idea. So you see, we have to fill, essentially, we have to compute the values in the cells. Right, so we have to fill this table and to eventually get to the top right corner, to get up there. And you see that you are able to fill, to populate a cell if you have been working on the cell to the left, the cell below, and the cell southwest. So you can do that in many ways. Of course, you can go column by column, right? So start with this column, then that column, right? So move column by column from left to right. That would work. Or you could work row by row, right? From the bottommost row, then the row above, and so on up to the top row. Or you could have a more complex way to travel. You could start with this cell, and that cell, and this cell, whatever, right? Whichever way of traveling that visits all cells gets you there eventually, and is such that when you get to a cell, you have visited before the cell to the left, below, and southwest, right? So something is absolutely clear. We have a base case, because you see I put a dot here because amongst the initial segments of the words, right? So depart, deep, D, all those are initial segments, but also the empty string, right? The empty word is initial segment of any word, right? So how can I convert the empty word into the empty word? By doing nothing for cost of 0, right? And then how can I convert D into empty word, DE into empty word, DEP into empty word? Obviously by deleting 1, 2, 3 letters, right? So there's a cost of 1, 2, 3, 4, 5, and 6, right? To map each of these initial segments into empty word, and obtained by, I come from the left and I delete, right? So horizontal arrow means deletion. It means I come from the left, so I mapped this to that. So to go to the right, I just need, because I mapped I mapped this into that. So if I move horizontally by one cell, it means I just need to delete the extra letter in the new initial segment of the first word, right? Similarly, the first column is straightforward, right? So I can map the empty word into L, then into LE, then into LEO by adding one more letter, right? So for a cost of 1, 2, 3, 4, 5, 6, and 7. Okay, straightforward. So if I decide to go row by row now, okay, so how can I map D into L? By moving horizontally and adding D for a cost of 1 plus 1, 2, or by moving vertically from bottom to top by inserting L, right? So I map D into empty, and now I have to map D into L by just inserting L, so for a cost of 1 plus 1, 2, or by changing d into L for a cost of 0 plus 2, 2, right? So the cost is 2, and I achieve this cost of 2 by coming from either direction, right? dE, again, I can come from the left for a cost of 2 plus 1, 3. I can come from below for a cost of 2 plus 1, 3, or because D and L are different, I can come from southwest and apply a change for a cost of 2 plus 1, 3. So again, a cost of 3 that I achieve coming from any direction. And on it goes, right? So I guess since there is no L, you see the cost will be 4, 5, 6, 7 coming from the 3 directions, right? How do you map D to E? To LE, sorry, how do you map D to LE, right? By coming from the left. So having mapped MT to LE, we mapped D to LE by just deleting D, so for an extra cost of 1, 2 plus 1, 3. Or I can come from below, 2 plus 1, 3, or 1 plus 2, because D and E are similar, so same thing, cost of 3, moving diagonally. And here, things get a bit more interesting, right? Because I can come from the left, 3 plus 1, 4. From below, 3 plus 1, 4. Because E and E are the same, diagonally, no extra cost. So I was there for a cost of 2. So I can get to this cell. I had mapped D. I transform D to L. I can now transform DE to LE by just matching both E's, right? So no extra cost. So you see that here the solution, optimal solution is 2, and it's obtained only by moving diagonally, right? Coming to the left, the cost will be 4. Coming from below, the cost will be 4 as well, right? So I could go on and on and on. I hope you got the idea. My scribbling is not great, so of course this is done in a much cleaner way. Right, so we went up to this point, right? DE to LE. Right, so you see we keep doing that all the way to the top right corner, right? So of course the number we find in the top right corner is the distance, right? It's the cumulated cost of all the transformations we had to apply to transform the part into leopard, right, optimally. So first we find the cost, right, the distance. And then how do we find the solutions? See, that's why we indicated in the cells not only the cost, but also the directions, right? Because now we can say, well, how did we get there? We got there by coming from the left, or coming from below, or coming from from southwest, right? In other words, all solutions to map depart to leopard will be given by all solutions to map to go there, and then the last step will be to delete T, right? Or also plus all solutions to come there, right? And then the extra step will be to insert append D, and all solutions obtained by getting to this point, and then I will have to change T into D, right? So you see, this tells you where to go to find partial solutions, and then you know what you have to do, straightforward, right? So either insert, delete, insert, or change, right? And this goes on and on, right? So now when you try to complement the solutions to this cell, how do you get the solutions to this cell? Because you have just a vertical arrow, it tells you that it's all solutions you get to map depart to leopard are obtained from all solutions to map the par into le pair, right, by just inserting D, right, and on it goes. So you see the number of solutions will begin by the number of paths, right? So this is a simple case, right? So this is deterministic, right? We have to follow this path, and to get there we have three options, 1, 2, 3, and to get there we have, and then at this point we have three ways to split to get there, right? So 1, 2, 3, 1, 2, 3, right? So of course 3 plus 3, 9. Well, that's what we said before. The multiplicity only comes from the fact that a change is equivalent to deletion and insertion, and to insertion and deletion, right? So because of the cost we give to change, the number of solutions is multiplied by 3 for every solution where we have a change, right? So that's it. That's pretty much the logic. Then the rest is just code. So I hope you've got the idea. So let's maybe start writing the code. So what do we want to do? So we want to implement a class. We could, of course, program that as a function, right? But essentially we want to define the class Levenshtein distance that inherits from object that will create a Levenshtein distance object from our data, right? So what are the data? Well, of course the data are the two words we work with, right? Word 1 and word 2. And then they are the cost. We could make it simple and use the cost we have been playing with, but to make things a bit more flexible, we could say insertion cost, set to 1, right? Deletion cost. Also, it's good not to put spaces when you have default values. And finally, change cost, right? We could make this argument only, maybe, as we did for previous problem and quiz 7. Let's not bother with that here, right? So we just need essentially to record these parameters, right, as attributes of an LD object, right? So essentially make all these arguments to init, things that we remember and that we'll be able to use in all other methods, right? If we, so it's good practice, of course, to give them the same name, right? Right, so you understand this is the argument of the init function, right? So something that we provide as an argument when we create an object, and this will be an attribute of the object, right? So if you don't remember it, of course, any method of any LD object won't have any way to access these guys, right? So we create these attributes. Deletion and change. Okay, and Okay, so we have now to decide whether we want to have a lazy or greedy approach, right? Obviously, we're interested in building this table, right? Obviously, we're interested in knowing the cost, the Levenstein distance between these two words, right? So we can either do that as soon as possible, so when we initialize the object, or later on demand as requested by a particular method. Well, you see, it's clear that for this particular example, class doesn't really give us much, right? It's clear that a simple function would be perfectly fine, right? So that's what I mentioned before. Don't think that you have to write classes for everything, right? Because essentially we want to know the distance. Once we know it, that's it, right? Then we want to know the solutions, but we know them, that's it. And what else? Nothing else, right? So things we want to compute once and for all. So from this point of view, having an object is not indispensable. All right, so let's say that we have this eager approach. So we build, let's say that we build a table, right? So we are going to have a table that other methods can use if they need. So since this is internal attribute, it's not meant to be something the user would naturally use, right? So good practice to start the name with an underscore. So that's something we compute, right? Compute the table. So self compute stuff. Okay, after all, that's so distances and the solution essentially. Well, build table. Okay. Self. Right. Right. So then we can build, of course, the object, right? To go from depart to clipper. And now we just have attributes, nothing else. Where on is depart? Okay. So how do we build this table, right? So of course we need a list of lists, right? So we have the choice between having a list of rows or a list of columns. Of course, this is just the way we think of our data, right? In Python, a list of lists, it's a list of lists. It's not a grid, right? So we have to decide how we want to interpret our list of lists geometrically for us to think more easily, right? Either as a list of rows or as a list of columns. But it's just a mapping from code to our own representation, nothing else, right? So let's say that we want to have a mapping. Let's say that we want to have a list of columns, right? Read from bottom to top, right? That's what I want to think. I want to think of a list of columns, right? And every column will be read from bottom to top. That's visualization of this list. So you see we have, so that means a list of size, number of letters in word 1 plus 1, right, because of this dot, because of this empty word, the empty initial segment. Right, so that's the outermost list. That's a list of size, number of words, number of letters in word 2 plus 1. Okay. So N1 will be the length of first word plus 1, okay, because of the empty word, empty initial segment. N2 will be this, and then my table will be a list of lists having, again, right, N1 elements, right? N1, that's length of depart plus 1. I think of my list as being a list of columns, right? So a range of N1. That's the list I want to have, whose elements are lists with N2 elements. Okay. So now what are the members of the inner list, right? So this is the columns. What do the columns consist of? Well, the columns, as we say, have to consist of two pieces of information. First, the cost, or the minimal cost to get to this cell, and then the various ways to get to this cell, right? So coming from the left or from below or from southwest. Okay, so it's a pair essentially, right? It's going to be a pair. The first element will be, let's make the cost the first element. Of course, when we start, the cost is all 0, right? Make the cost equal to 0. But actually, it doesn't matter because we compute it, so we could make it none. Okay. And then we could have a list, or we could have a set of directions. Right? Let's see that we have a list of directions. Right? So we initialize with, we come from nowhere. Right? So our table initially, all the cells cost of 0, and we didn't access any of these cells, so 0. Right? Correct. And why is not defined? Either I use an underscore or I don't. One or the other. Okay. So, well, we do what we did, nothing else, right? So we started by initializing the first row and the first column, right? So the first row, well, start with the first column, right? The first column is the first list, right? So that's table of 0, right? That's the first column, first list. And we look at all levels of this column, right? So for I in range of n2, right? So at this level in our column, we change the cost to I, right? That's level 0, 1, 2, 3. The cost is equal to the level. And the direction is by moving up. So you could have an up arrow as a unique character, or it's the vertical bar that will do. Correct? Okay. It's pity it doesn't display it. Of course I could print it, right, in a nice way, but hopefully that's fine. Right, and then we want to initialize the first row. So that's when the second index is equal to 0, right? The second row, it's all, I have a list of lists, list of columns, right? So each, I have to look at the first element of the columns, right? So second index equal to 0, and the first index ranges from 0 up to a length of the part. So, and 1 table of I0 is equal to I, so that moving horizontally, right? So you see, this is the row, right? This is the first row, right? Because I have a list of columns, right? So the first member of each list makes up a new element of the first row of my representation. Okay, and now I have to compute the rest, right? So for anything else, so I can compute, as we said before, in many ways. I can compute row by row, column by column, right? So I guess for me it's easier to compute column by column, right? Because I make column by column, because I will make I range from 1 up to the length of the first word, right? To scan all the columns from left to right after the first one, for I in range of 1 up to n1, and for given I, for given column, I will have a look at each of the rows in turn, right? So I will go from bottom to top, starting from level number 1 with level number 2. Level number 0 is done already, right? So I first select a column, then I move in this column from bottom to top with the second loop. Okay, so what do I have to do? So remember, I have to see, I have a lot to do, right? I have to look on the left, I have to look below, I have to look diagonally, at least if I can, because these indices are at least equal to 1, so that's fine. And whatever I find on the left, I need to compare the three numbers, right? So remember, I store pairs, so the first member of the pair is the cost, so I have to look at that. And then I have to look at the directions. So maybe it's useful to work with a dictionary, right? I could work with a dictionary whose keys would be the directions, right? And whose values would be the cost. Right, so we can have a dictionary. I don't have to initialize the dictionary within the loop because I'm going to override the value essentially, right? So it can be defined, initialized once and for all outside the loops. And now I can have a look at okay, coming from the left, what's the cost? Right, what is the cost of coming from the left? Well, my table at location I-1, right, that's I is the column index at the same level, level J, right, is a pair whose first member is the cost. Right, so that's the cost of reaching the cell to the left. So to go now to the current cell, I need to add to that self dot deletion cost. Okay. Then my dictionary has a key for the other direction, which is coming from below, right? So I'm the same column, but I come from the row below. And so the cell just below has a cost given by the first member of the pair, and the cost of getting to that cell, right, is increased by 1 by this to get to the cell just above. And most interesting, of course, is moving diagonally, right? So I look in the previous column, previous row, cost there, and either that's the correct cost in case now an intersection of column I and row number J, I have the same letter. Right, remember, so if my first word, so remember I is column, right? So that's I is index of columns, right? So it's the index I use to retrieve the corresponding letter of word 1. Right, and J, that's the index of the height. Right, so J gives me the index where I find the corresponding letter, the letter at that height for the second word. So if now I have to be careful. Alright, because remember we have the empty word. So index 0, that's for the empty word, right? Index 1, that's for the first letter of the word, right? So which is indexed by 0. Index I equal to 2, so the third column, right? That's for the second letter in my word, which has an index of 2. Of 1, okay, minus 1. So I have to decrease by 1, okay, because of this empty initial segment. right? The shift of the index of the letters of the words are shifted by 1 compared to the indices of the columns and the rows. So that's what we have, right? Else, so it's equal to this if the two letters are different. Otherwise, it's equal to this plus 1. Okay, so after I've computed the cost of coming from the left, coming from below, and coming from southwest, I see what's the best cost, right? So best cost, that's the mean, right? So that's the mean of my dictionary. So I can take values, right? I have a dictionary like this, E equal to something like that, right? That's the cost of 2, let's say. That's the cost of 2. That's the cost of 3. Okay, so how do I find the minimum cost? Well, I can get all values in the dictionaries, right? And then I can take the mean of that. 2. Right, so it's mean of d dot values. And now what do I put in my table at location ij? Right. Well, I put a pair, right? The pair is first the cost, and the second element is the list of all directions that give me this cost, right? So in other words, it's the list of all keys of the dictionary that give me the cost, right? So it's the list of all directions, x, whatever, for x in D, right? D dot keys, but as you know, this is the same as D, right? In case my dictionary for this key D give me a cost equal to best cost, right? Makes sense? I'm looking just at the list of x for x in D if x and D dot x equal to this. Alright, so I get, it's for the keys, hyphen, and slash, where the cost is minimal. Okay. Okay, and then how do we get, so we could immediately compute in init the distance, right? So 11 hash distance between both words. What is it? It is what's in the top left corner, right? So in the top, in the last column, and in the top row. So I don't need to return it, right? Yeah, yes, I need to return it, of course. But how I can just have a look at this new attribute, right, distance of the object I just created, right? So when I create the object, initialize the key data, right? Then I call the function to give me the table we built, and then I retrieve the cost. So it's not exactly what I want, right? This is a pair, right? I don't want a pair. So it looks like we made something wrong. So it should not be 3. What's wrong? Yeah, it's not +1. It's +2, which is change cost. Right. Change cost, which is 2. Oh boy. 5. And we only want the first member of our pairs, right? We just want the cost. Okay, so we computed the level shine distance between both words, right? And then it's a matter of getting the solutions, right? So it's a bit of extra code. I'll let you look at the code yourself. It's a very interesting application of generator functions. So let me just maybe comment on the code. Right, so that's what we did essentially, right? More or less, that's what we did. And then we find it convenient somehow. You see, once we have found the cost in the top right corner, right? To find the path, to find the path, you see, we just have to follow the arrows, right? Starting with the top right corner, right? And making our way to the bottom left corner, right? So now the only thing that matters for the solutions is the arrows, right? It's not the numbers. The cost, the only point of computing the costs is to get the cost in the top right corner, the distance. Once we have that, all the other costs will just help us to get there, right? They have no purpose by themselves. They don't present any interest. So we can actually create a new table, right, where we just keep the directions to make it a bit simpler to work with. Right, so that's what I do there. You see, I define a new list of lists, right, we call backtraces, which is essentially the second member, right, the member of index 1 of the pairs that make up all the members of table, right? Remember, table of I of j, that's a pair, cost, and then list of directions. List of directions, that's the element of index 1. So essentially I create a new list where remove, well, you got it, right? A new list whose members are not pairs, but consisting of a cost and a list of directions, but that's just a list of directions. All right, and this is the magic function, right, that computes the alignments, that computes the solutions, right? So it's really worth for you to study this function in depth, and of course in the notes I always write things in much more detail, right? So I trace execution, you see. So if you, I show exactly how it's computed, right? So if you have difficulties with the code, I encourage you to study the notes. They really explain how things are executed, right? But as you remember, when you look at recursion, you can think of it at a high level or at a low level. At a high level, right? So how things work for a problem of size X, assuming it works for a problem of a smaller size. At a low level, it's how all the codes are executed, right? In which order, one after the other. right? So here we want to essentially get all solutions up to the point of coordinates ij, right? So column I, row number j. Of course, this is interesting when this is the highest possible, so n1, and this is n2, right? Then we're done. And each of these, the recursive calls, you see, it's a recursive function, right? That makes the problem smaller and smaller and smaller by decreasing, of course, the one or two of these arguments, right? So by looking at the column to the left or looking by the row below, right? Until base case, we have reached the lower left corner of the cell, right? When we match the empty string to the empty string. Well, of course, to match the empty string to the empty string, we just need to say we transform the empty string into the empty string, right? So we yield, it's a generator function, right? Much more efficient than creating a list and returning the lists. Now, if it's not the base case, so at least one of I and j is not equal to 0. We don't need to test whether I or j is equal to 0, because at location ij in our grid, remember we have a list of directions, right? So if this is part of the list, it means we were able to move diagonally. So it means that both I and j are strictly greater than 0, right? If in our list we have the hyphen, it means we could come from the left. So it means that I was not equal to 0. And same thing for that, right? So essentially, we were able to come to this position, ij, right? Coming from southwest, left, or below. Yes or no? If that's the case, if we could come from southwest, right? So you see, we ask to get all solutions up to the cell below to the left, right? So we decrease both I and j by 1, because we were able to move diagonally, right? So if we move diagonally, we come from there. And for pair in this recursive function, you see, it's a generator function, right? So it's going to activate yield. It's going to give you all the solutions, right? In the form of pairs, in the form of I was able to map this word to that word, this initial segment to that initial segment, right? This initial segment to that initial segment, right? And now maybe it's not very clear. It's going to return something like I was able to map D to Leo. It's going to return this, right? This kind of pair. I was able to map this to that. Now you move diagonally, right? Because you could map deep to Leop, right? So you need to complement this solution with deep and Leop, right? In other words, you need to add p to both sides, right? So that's pair, that's what is returned by the recursive call, right? That's pair of 0, and that's pair of 1, right? And you see, you expand pair of 0 and pair of 1 with the letter, right? So that's what I said, right? Pair of 0, pair of 1, and then you complement that with a new letter, right? Which is what you find in the first word for the first pair, in the second word for the second pair, to get to cell ij. Remember, because of the empty string, right? The indices are shifted by 1 when you look at positioning the words. That's all, right? Understand? So self.word1 of n-1 in this particular case, right? That's the letter P. Right? So we just do DE plus P, and here we just do Leo plus P, right? to get these new strings. Okay. And the same thing, of course, if we came from the left, that's because we have been able, we just have to, for any solution where you come from the left, so for every solution when you come from the left, we have to delete this new letter, right? So that's how we indicate it, if you remember what we did at the beginning. Oh no, it didn't just show it on the PDF because it's much cleaner. Oh, that's what I said. Okay, here we insert O, right? And here we insert, here we delete D, right? So you see, when we show the solutions, when we delete a letter, we show the letter we delete in the first word, and we give a hyphen at the corresponding position in the second word, right? When we insert, it's the other way around. When we insert, we put a hyphen in the first word, and we put the letter we insert in the second word, right? So here we delete, so we show the letter we delete in the first word, and we show a hyphen at the location in the second word, right? So well worth understanding this function, and again the notes help you with extra code if it's not clear, but it's a very good application of recursion. Right, so I've been a bit long on that, but I think it's important because it's essentially the assignment, right? So what we did, you see, building this table is exactly what we need to do, and I just need to massage a little bit this code. Don't be concerned by plagiarism. You won't be caught by plagiarism if you copy and paste this code and massage it. I expect most of you to do that, of course. And yeah, that's it.